As I said, we're going to now turn to what's known as an inelastic collision. An inelastic collision in one dimension between two objects differs from an elastic collision in the fact that the internal kinetic energy is not conserved. That is, there is a loss of kinetic energy outside the system. So, for example, internally in the first part here, you have a certain amount of internal kinetic energy which is related to these two masses. And when they collide and they have momentum, and this is all before, when they collide, the sum here has to equal the sum here. And what they're showing here is that with an inelastic collision, because they both just stop, the internal kinetic energy goes from the sum of the two, which is mv squared, 1/2 mv squared plus 1/2 mv squared is equal to mv squared. The v's, because they're squared, this negative becomes a positive, and this turns into 0. And so the kinetic energy is not conserved, although the internal momentum is conserved. The objects stick together and their final velocity is 0. The internal kinetic energy changes from a positive amount to nothing. So we have a situation now. Here's a goalie. Here's a hockey puck coming at a velocity, and the mass of the goalie is represented here. And before this goalie is not moving, so the total momentum is equal to the momentum of the puck. The total internal kinetic energy is equal to the kinetic energy of the puck. The goalie is not moving. After he catches the puck, then the new momentum is going to be equal to the sum of the two, the goalie and the puck. And this new momentum total has to be equal to the old momentum total. However, the kinetic energy, internal kinetic energy of the before the collision is going to be greater than the internal kinetic energy after the collision, because something is lost in the transfer. So let's take a look at that. So here's the numbers. The goalie weighs 70 kilos, the puck weighs 0.15 kilos, and is traveling at 35 meters per second. It asks how much kinetic energy is lost after collision. So we start out, we have the sum of the momentum before is equal to the sum of the momentum after. Therefore, you break that down and you can calculate from this. Simplifying, you have the velocity of the goalie after he catches the puck. He catches the puck, so the new mass is equal to the sum of the two. He catches the puck, so his velocity is 7.48 times 10 to the minus 2. The kinetic energy, on the other hand, is the internal kinetic energy is 1/2 mv squared, which before the collision is 1/2 times the mass of the puck times its velocity squared, or this value here, 91.9 joules. After the collision, it's 1/2 m plus big M for the goalie times the new velocity squared. We put the big M is now 70.15, and the new velocity is given here squared, and we have a total kinetic energy of 1.196. So lost in the translation with the collision is minus 91.7 joules. Remember in the previous, when the two blocks collided, it went from a positive kinetic energy to 0. So there's generally a loss of kinetic energy when there's an inelastic collision. So let's take a look at a couple of problems. The first problem is here. A 6 times 10 to the 6th kilogram battleship at rest fires an 1100 kilogram shell horizontally at a velocity of 575 meters per second. What is the recoil velocity of the ship? And what is the increase of the kinetic energy of the ship in the shell? Now the difference here is because you start with both the ship and the shell at 0. Neither is moving, and then the shell is fired. You have an increase in kinetic energy when that happens, as opposed to the situation where two blocks are moving and collide and stop. You'll have a decrease in kinetic energy there. So let's take a look at how we would do this. Okay, so we have the first mass is the mass of the battleship, and that's going to be equal to 6 times 10 to the 6 kilos. The mass of the shell is 1100 kilos. Now, before the shot is fired, neither of these are moving, so the initial of both of these is 0. So after the shot is fired, this is what we want to find, and the shell is traveling now at 575 meters per second. And so the sum of these has to equal 0, because before they were equal to 0, now the sum has to be equal to 0. So 6 times 10 to the 6th times V1 plus 1100 times 575 has to equal 0. And so V1 is going to be 1100 times 575 divided by 6 times 10 to the minus 6, or plus 6, excuse me. And this is going to be a negative number because it has to be in the opposite direction. If you do the math here, you get 0.105 meters per second. And it's negative because it's in the opposite direction of the shell. Now, before, neither of these were moving, so the initial kinetic energy was 0. After, you're going to have 1/2 times the mass, which is 6 times 10 to the 6th, times v squared, which is 0.1505 squared, plus 1/2 times 1100 times 575 squared. And this whole business here works out to 33,075 joules. And this works out to 1.818 times 10 to the 8th joules. Now this is so much larger than this that this is negligible. So the answer is 1.81 or 2 times 10 to the 8th joules is the increase in kinetic energy when you fired the shot. Okay. Now let's take a look at this second one, which is a little bit more complicated. I'll make it bigger first. Pu-239 decays to form helium and uranium. When this occurs, it produces this amount of energy, which is converted into kinetic energy. If the mass of the helium is this and the uranium is this, and the Pu is at rest before it splits, what is the velocities of the two nuclei? Now this one's a little bit more complicated than the last one. And what you have to see is that the two are not moving. Okay, so the initial momentum is 0, and so whatever you get afterwards, m1 v1 plus m2 v2 after, also has to equal 0. So the momentum of the helium nucleus moving in one direction has to be the same and in the opposite direction as the momentum of the uranium nucleus. And so what that means is that the mass of the helium nucleus times its velocity has to equal the mass of the uranium nucleus, which is 3.92 times 10 to the minus 25 times its velocity. Okay, and obviously these are in opposite directions, so one is the negative of the other. And then the second thing is that the kinetic energy of these two, the sum of the kinetic energy of these two, has to equal the kinetic energy generated by the separation, which is 8.4 times 10 to the minus 13 joules. So we have 1/2 times 6.68 times 10 to the minus 27 times V1 squared plus 1/2 times 3.92 times 10 to the minus 25 times V2 squared has to equal 8.4 times 10 to the minus 13. And again, now we have two equations, this one and this one, and we have two unknowns, V1 and V2. Now I actually didn't go through the trouble of figuring this one out for the sake of time, because it's fairly complicated, but you can basically move this over here and then put this in one of these two and do the same solution as we did in the last one where we had two equations. Now lastly, let's talk about collisions in two dimensions. Remember that I said that momentum is a vector quantity. Because it's a vector quantity, all momentum can be broken down into its x component and its y component, just like we did with velocity, just like we did with some of the other things that we worked with. And the x component has to be conserved and the y component has to be conserved. So when you have a two-dimensional collision, you have a collision like this, all of the initial momentum is in one dimension, shown here. It's in the x dimension. The x amount on this side has to be equal to the x amount here. The y amount has to cancel each other out, because the y amount has to add up to 0, because there was no y amount before the collision occurred. And down here it shows the angles, the cosine of the angles is the calculation of the x component. Sorry about that. So the x component of the first ball is this one. The x component of the second ball is here. The sum of those has to be the x component before the collision occurred. And that's where that comes from. So here we have a 0.25 kilogram object, M1, and it's slid at a velocity of 2 meters per second into a frictionless into a dark room and collides with a object whose mass is 0.4 kilograms. M1 emerges at an angle of 45 degrees and a velocity of 1.5 meters per second. So it's asking what is the mass, or what is the velocity and direction of M2. And what you have here is the y component of M2 has to equal the y component of M1. Okay, the y component of this velocity and the y component of this velocity has to equal M1. And the x component, the sum of the two x components has to equal the x component delivered here, which will be 0.25 times 2. And so if the incoming object is scattered by the initial solitary object, only the solitary object's mass M2 is known. By measuring the angle and speed of M1 emerging from the room, it is possible to calculate the magnitude and direction of the solitary object after the collision. And so we can do that by using x and y components. And here we have M1 V1 is equal to M1 V1 prime cosine theta, that's the x component, M2 V2 prime cosine theta, that's the x component of that. So the sum of those two x components has to equal this one. And we also know that 0 has to equal the y component of the two. And that's how you calculate it. So let's do a couple of actually, let's move on to the line. No, let's do a couple of problems. 3,000 kilogram cannon. It can only recoil in the horizontal direction, so only in the X component. Calculate the recoil velocity if it fires a 15 kilogram shell at a velocity of 480 meters per second at an angle of 20 degrees above the horizontal. And what is the kinetic energy of the cannon? So let's take a look at this one. It's 3,000 kilograms. The mass of the cannonball is, 15 kilograms. The velocity is 480 meters per second, and the angle is 20 degrees. So it can only go in the X component. The X component is the cosine. So M1 V1 of the cannon is going to equal M2 V2 of the cannonball times the cosine of theta. And so V1 of the cannon is going to equal all this divided by M1. So this is going to be 15 times 480 times cosine of 20 degrees divided by 3,000, and that's going to equal 2.255 meters per second. The kinetic energy of the cannon is going to equal 1/2 times 3,000 times 2.255 squared. And that's going to equal 7,630 joules. The second problem here, if we look at the second problem, two identical pucks collide on a hockey table. One puck is at rest. If the incoming puck has a velocity of 6 meters per second and scatters at an angle of 30 degrees, what is the velocity, magnitude, and direction of the second puck? Assume that the sum of the angles is 90 degrees if the collision is elastic and the masses are identical. Now this is actually a lot easier than it looks because it tells you to assume that the masses are identical. Okay, so what you have is you have a puck, we'll call it M1, it's traveling in at V1. You have a second puck, M2, and it's sitting there. It hits, and the first puck, M1, ends up down here, and this angle is 30 degrees. The second puck goes this way, and this total is 690, so this angle is 60 degrees. And so what that means is that M1 V1, which is the X component before the striking, is equal to M1 V1 prime cosine 30 degrees plus M2 V2 prime cosine 60 degrees. And M1 V1 prime sine 30 degrees, the Y component of that, has to equal M2 V2 prime sine 60 degrees. Okay? Now, because these are all the same weight, if they were, say, 1, they basically end up canceling each other out. And so you end up with V1 prime cosine 30 plus V2 prime cosine 60 is equal to 6, which is V1 here, because we canceled that out too. And you also know that V1 prime sine 30 is equal to V2 prime sine 60. You have two equations and two variables. And if you do the math here, v1 prime ends up being 2.4 meters per second, and v2 prime is equal to 4.15 meters per second. And obviously this v1 is at 30 degrees south of horizontal, and or down from horizontal, and this is 60 degrees up from horizontal. Okay,